Welcome to the Energy InSites podcast, your source for the latest insights in deep retrofits, renewable energy, and energy conservation. And now let's get to today's insights. All right, hello and welcome to another episode of the Energy InSites podcast. With us today, our distinguished guest, Robert Bean. Nearly 40 years in the HVAC industry. Lots of wisdom there to unpack. Robert, welcome.
Thanks for having me on. Much appreciated.
Yeah, so take us back a little bit to young Robert. Maybe you can kind of give for our audience that doesn't know you a little bit of background on kind of how you got into this space and how it's evolved and kind of what your passion within HVAC has been, and just tell us a little bit about yourself.
Well, it started when my dad sat me down at an early age and said, "Robert, you're basically unemployable. You better find a career path that you can make some money to pay for food and board." So I started out in the construction industry a long time ago. My dad was a chartered accountant, but he was involved in home building as well. And so I remember as a kid, like 8 years old, 7 years old, crawling around construction sites, and the smells of the dirt and the cut lumber and the form oils and all that kinds of stuff, and that has stuck with me for my entire life. So I started out actually in the trades, and then, but before that, I went to school. I was taking surveying, and I think it was my first term or something like that, and I actually went away on a holiday, and I was lying on the beach, and I looked up at the sky and I thought to myself, if I graduate from the Southern Alberta Institute of Technology surveying program, I'm going to find myself in Northern Canada holding a stick in 3 feet of snow with no women around. So, I said, I don't think I want to be a surveyor. So anyways, and then from there, I actually ended up working for a geotechnical engineering company, a piling foundation company, and then framing, cribbing, and then I went to school and graduated from the Building Construction Engineering Technology program at NAIT. And then, and when I graduated, there was the Alberta Energy Program and Ottawa. There was no love between Western Canada, much like today. And basically, all the drilling rigs pulled out of Alberta. It basically collapsed our economy, and so there was no construction jobs. Somebody was looking for a solar engineering technologist, and I didn't know anything about solar engineering. But I went to the library. Some young people might not know what that is, but that's a place where they hold books. And read as much as I could about solar, and then had drafted up a solar heated home and submitted that with my resume, and I got the job. And it wasn't much longer, the owner came in and said, "You don't know what you're doing, do you?" I said, "Not really." And he said, "I don't know whether I should fire you or keep you around for your chutzpah." So I ended up sticking around, and I ended up buying part of that business, sold it, bought another business, and I got into the mechanical side. And through that, the world opened up, because back then when I got into the mechanical side, there was district energy projects that were coming up. There was a company called FAB out of Sweden that came to Edmonton. Actually, they were going to do a district energy off the power plant downtown, and we were a distributor at the time, and of some pretty great thoroughbreds in our product line. Like, we had some of the best European stuff that we were marketing, selling, and engineering systems with. And he got a call from this Leif Erikson guy in a Swedish accent, can you make shit? Well, when an engineer calls you up and they're building a big district energy system and you've got all of the toys, and he says, "Can you make stuff?" Well, there's only one answer. Yeah, we can make it. I didn't have anybody on staff at the time that could make stuff, but I would find a way to make it happen. So we got into the substation business. We were starting to make substations, and we were selling components and all of that. And then we grew that business, and then ultimately I sold it to Danfoss. Actually, it was a Danish company, and they bought that business in I guess it was 2000 or something like that. So I was still a young man. I was too young to retire.
And when you say substation, you mean actual like electrical
No,
equipment
these were
or
mechanical, so heat transfer stations. So
heat
when you
transfer?
do district energy, you've got this central plant and it's sending water down through these corridors, typically under the sidewalks. And then each of the
Mm-hmm.
buildings plug into these networks, right? So you've got these heat transfer stations between the distribution piping and the building. So we're
Got
talking
it.
flow meters, pressure regulators, temperature regulators, heat exchangers, all that kinds of stuff. So we
Your
were making,
manifold network.
yeah, so
Yeah.
big stuff. And then the bigger buildings had energy meters on them, like mag meters and these types of things. So, and what we found from that is that because these were pre-engineered substations, so there was typically a consultant on the job that was doing the engineering. So what were the characteristics of the system before the building plugged into it, right? So we would design all of that and then make it and then get it tested in our laboratory. And when that went out into the job site, it was like a stick instead of a boomerang. And what I mean by that for your guests is that when you engineer and manufacture stuff and you ship it out the door, you don't want it back. You want the money.
Right.
That's how it works, right? You build the stuff, you ship it out, you get the money. Now the transaction's done, right? And if you do that right, you put profit in, into your business, and the share value goes up. So, anyways, when we sold components, right, it was the boomerang. Like we would get stuff back all the time because people didn't understand how to fit it or wire it or whatever, right? Like,
Mm.
so we had you're constantly, the parasitic losses on your profit sheet were constantly being tested because people didn't know how to do stuff.
Wow.
And then even though we had education programs. Anybody that knows me knows that for 40 years I've been teaching. We had education programs coming out of yin yang, but people would still do stuff that was, you couldn't believe that these were, anyways, doesn't matter. When you pre-engineer stuff and you prefabricate it and you test it and then you ship it out and it works, um, it's the way to go. So, that's a whole discussion there right now in terms of prefabrication, whether it's
Yeah.
mechanical systems, electrical systems, or buildings, because we have to find a way. The construction industry is like so far behind. You know, like Boeing can crank out a 747 way faster than you can build a house. I think Toyota puts out a car every couple of hours, right? Even these
Right.
massive cruise liners, like you can put a full modern day cruise ship, and you think about that, right? For thousands of people, so they've got kitchens, they've got sewer systems, they've got communication systems, they've got navigation systems, all the power plants, right? These are massive, massive floating communities, and they can crank one of those out every 2 years. Like it's just, prefabrication is everywhere in our world except in construction. It's actually bizarre. Anyway, so going back. So I
Yeah,
sold
that's a
that
good one.
business.
That's a good one for us to keep going on a little
Yeah,
bit later.
absolutely. It's one of my favorite subjects. And then so I got into the engineering business, and we started to apply typical standards, ASHRAE standards, the CSA standards, codes. And even though we followed everything to the T, we would still have people calling us about, well, it's cold in here or it's too bright or whatever, right? And I just by chance was doing research work, like why when we do things to codes and standards that we still have people unhappy. And I came across this Dr. David Shetzley from Arizona State University, and he had this thing on his website, the Arizona State website, about like almost like biophilic design, bioclimate design. And he had these pages on like human physiology and psychology that related to the built environment. I went, whoa, wait a minute, I didn't
Hmm.
study any of this stuff going to school. So I had time because I had sold the business. And so I went on a journey of learning about human physiology and psychology. And I took every medical course that they would let me in and sit and audit without, actually being a medical student. And I read books, and anytime I
Wow.
had a chance to talk to a physician or whatever, I could just learn like why does the body perform this way, and quickly learned that there's this huge gap between architecture, construction engineering, and people and the way that we sense the environment with our sensory systems. And I said, well, let's use the human body as the design model for architecture. And that's design around it, right? As opposed to client goes, hires an architect, architect does up the design, hands off the design to the mechanical engineer and says, okay, now make it work, right? we flipped that on its head. We just said, well, hang on, this is what the body needs and the mind needs. So it needs this kind of lighting, and it needs these sounds, and it needs these thermal environments, right? And when you create those environments, then the body has less stress response. And so we can design that into the buildings with good architecture, good enclosure, good interior systems, and then properly selected mechanical systems. So when I say that, it means that if you have a convective problem, then solve it with a convective solution, but don't try and solve it with a radiant solution, or vice versa. If you have a radiant problem, solve it with a radiant solution, but don't try to solve it with a convective solution, which is what we typically do in design. And that never works, right? So when we figured this all out and started to apply this in our practice, literally the next generation of buildings that we released for construction, like it was night and day. People came back and said, we had no idea you could have a building, an interior space that was so amazing. You know, the sounds and the lighting, the thermal environment, the air quality, all of that was just because we designed it to cater to the body's needs,
Sure.
right? And so having a trades background, a construction background, mechanical engineering background, and then an understanding of human physiology and psychology, I started to talk about it. And well, people were paying attention, so they would hire me to go talk. And then I became an ASHRAE distinguished lecturer, and I traveled all over the world. And last count, I have left the Calgary International Airport over 360 times to do lectures about integrated design. And that's another thing. Like when people use the word integrated design, it's like their brain stops at the design, the traditional design, like architecture, engineering, blah, blah, blah. They don't talk about the people, but ultimately it's the people that are the sensory system. People are the feedback loop. So when I hear
Right.
people talk about integrated design, I just want. Like, where's your discussion on the very people who are going to pass judgment on your design work? If you're not including them, you're not integrated. You're just creating another silo, and you're excluding the very people that are going to be operating or living in the building. So
That's really
let's stop doing
interesting.
that. Yeah. Anyways,
Yeah, we when we think integrated, you really just kind of your mind goes to architectural, mechanical, electrical, plumbing, integrated,
yeah,
right?
right.
And then it's like, oh, what about the people?
Yep, yep. So that's the story, and this June actually I'm going to be retiring from I think that's probably the first time I'm publicly going to say that is this June I'll be retiring from the program, and it's been a long era, many decades traveling all over the world, and I've met some great people, and we're making a difference. And one of the things that really sort of boosted our messaging was when Bill McQuay took over this year's ASHRAE presidency. So the 25-26 presidency was all on indoor environmental quality, healthy buildings. And so Bill has been traveling around the world, and part of that work was to develop resources. So if you go to the ASHRAE website now, and you can go to the indoor environmental quality section, and there's a section there for lighting, sound, air quality, thermal comfort. We've now added water quality, the microbiome onto those terms. And you can go there, and it was just a group of us, a handful of us, that over a period of time leading up to Bill's presidency, that we just put together. Basically, it was a mind dump. It was just like, okay, the world needs to know this shit. So let's just put it down on paper, get it out there, and show people how to access the resource, and then how to build onto their understanding what integrated design is all about. And it has to include the people. You can't have integration without the very feedback loop that's going to tell you whether you did your job right or wrong.
Well, that's really great. And we a lot of our listeners are kind of asset owners, asset managers, building operators, community leaders. So what would you say to folks that have a portfolio of buildings, whether that's residential MERBs or commercial industrial stuff, as a way of kind of looking at their existing portfolio and starting to have a healthy order of operations, a methodical approach to figuring out what they've got and what they should be doing next, and after that and after that? Like what kind of approach do you typically take to a
Yeah, so
project?
this
Or
is a really good question, and it's I wish there was a very simple answer, but Let's take an example out in British Columbia. If you go back into 2022, over 600 people died um, that unnecessarily. Some of them, yeah, we could have saved a lot of people in that heat dome. And the problem was is that the buildings were never designed to deal with these extreme events that we're now seeing everywhere around the world. People are in the denial of climate change. I don't use climate change. I use climate change as a consequence because I don't know enough about all of the things that can affect it. But when climate changes and it has a consequence, death is a consequence. You can't come back from that, right? So when we have people in buildings, existing buildings, and they're not designed to deal with these extremes, there is no other option but the indoor spaces to become very uncomfortable to the extent that they can start creating health issues, and in this case, cause death. And so, what do you do with existing architecture? Well, you have to find a way to understand what the problem is inside. Now, people are really good sensors and they will tell you, you have to listen to what they're saying, right? And, but sometimes people they don't have the technical jargon, which is actually a good thing. They'll use words like it stinks, smells, it's cold, it's drafty, it's loud, it's muggy, right? These are words that the vernacular architecture people on the street. Architects and engineers, we use different terms: fenestration, infiltration, U
Right.
value, connectivity, emissive, like all these technical terms, right?
Yeah.
And that's a problem. Like when it's great when you understand the lingo and you can talk amongst your peers, but when you're talking with the client base, you have to like start using their language. There's a principle in communication that the message of your meaning is the response you get. Well, if someone's looking at you with blank eyes, you can keep talking the same crap, but if they're not understanding, that's not their problem. That's our problem as communicators. So we have to use their language if we want to send a message. And so if they're telling us it's hot, okay, why is it getting hot? And right, and so well, every morning the great big oven shows up from the sky, dumps a whole bunch of shortwave radiation onto the building. Well, that shortwave radiation, right, solar energy lands onto the exterior of the enclosure. Some of it passes through the glass as shortwave radiation. It's high intensity, very heat, raise the temperature in the space quite easily. Some of it gets absorbed by the walls and the roof, right? And then it gets conducted through. And now we have warm surfaces. So you got warm surfaces on the roof, the ceiling, or the floor, the walls. And then you've got shortwave radiation coming through the glass. Well, a lot of people don't understand this, but we live in a world, unfortunately, that is dominated by this perception that air temperature and thermostats are proxies for thermal comfort, and they're not. They're actually the worst device ever made to represent what people feel. We know that almost 60% of the sensible heat transfer that people have with the environment is via radiation. It's not air temperature. And everybody can experience, let me just put this into sort of basic language. When you walk into an underground parkade in the middle of summer, like you're walking on the street, it's super hot, the sun's shining on you, you're just like, you want to get out of the outside and get into the inside, and you go into parkade and it feels cool. It's
Right.
not that the air temperature has changed. It's just that all of that concrete and the ground is at a cool temperature. The surfaces around you are cool. So you can discharge your body heat to these cool surfaces. That's actually what's going on. If you want to make
Wow.
it more sort of retail experience, next time you're in the grocery store and you're walking down the freezer aisle, the air temperature is the same as the aisle over. That's not a freezer section. But why does it feel cool? It's because all of those freezers, the coolers, are at a cool surface temperature. So your body's actually releasing energy via radiation to these cool surfaces. It's the energy leaving your body that provides the cooling sensation, right? So
Really?
that's
Wow.
what's going on. People don't understand that,
I
right?
would have assumed the air temperature was cooler in that
No,
little
you just
micro
walk.
region.
Yeah, and you can even like you can be like, for example, if you really want to make it simple, right? You're lying on the beach, right? The sun is shining on you, it's super hot, right? But a cloud then covers up the sun. Has the air temperature changed? Right? But your experience changes because the source of that energy has been blocked, right? So even though the air temperature has changed, you have different thermal experiences based on radiation. It happens, it's part of your life. Every day you wake up in the morning, you're going to get exposed to that. So So if you're a building owner and people are complaining, yeah, you can start, you can, and there's no air conditioning, you can put in air conditioning. And that's one of the problems that I see happening. It's just like it's a train wreck happening. And then the building codes, building owners are now required to have at least one room. Some of the codes, right? For example, in BC, where you have to have spaces that can be cooled to a certain value, but that value is air temperature, and they're ignoring the radiant element. So yeah,
Mm,
you can put in, have a refuge space where you can bring the air temperature down to whatever that number is. But if there's still shortwave radiation in that space coming through glass, you're still going to have a problem.
mm,
So it's really important that, so as a building, going back to your question, that trying to understand where's the problem. Solar energy radiant is one of the biggest problems that we have, and it's going to continue to get worse. So looking at how do we prevent all of this energy from dumping onto our building. So now we're talking about shading, we're talking about colors, talking about the science of materials on the exterior, using, you know, shades that are on the outside of windows, not on the inside, which is like one of the blessings I've had in my career is I've had to travel. I've traveled absolutely everywhere over 35, 40 years. In other parts of the world, they put the shades on the outside. There's a reason for that.
and
Shutters and awnings, and
right,
it's because once the energy gets through the glass into the inside of the
right.
building, like we do here in Canada and North America, it's now a load. But in other parts of the world, they don't let that happen. They're much smarter than we are.
Mm-hmm.
So putting the blinds on the exterior of the building, and I just came back from Australia and Brisbane, and I tell you, there's a community of architects and engineers and clients that totally get exterior shading. Like they've done such a great job there, keeping the radiation out of the building and off the building too. So anyway, so going back to your question, you know, these are things that they have to do, and then if you're not prepared as a building manager or owner to fix the architecture, keeping the sunlight off, then you're going to have to find a way to enable people to adapt to their environments. One of the ones that is most common is to use fans, elevated air speeds in spaces, right? And encourage people to dress with lighter clothing, stay hydrated, right? If they get into extremes, which we're starting to see, having people relocate for those extreme moments into parkades, north sides of the buildings, these types of things. Um, and then making sure that there's a system, of first responders or people within their community that can check on them. A lot of elderly people, sometimes they're not aware of actually what's happening, right? Or there's issues with them psychologically. They don't want to move. They don't want to. They become agitated, but they don't know that they're in a risk state,
Mm,
right? So part of it is the owners of the buildings doing what they can, providing means for people to adapt, but then also creating a network so that people can check up on their neighbors to make sure that if they are in stress, that we remove them from those environments and get them into places that are cooling. Most people have access to, a bathtub, for example, but they don't think that, okay, well, I'm getting hot, and so my cardiovascular system's going into a stress mode, and they don't think about, well, if you just go stand in the shower and there's some cold water, that would help, right? So,
right,
or
right.
cooler water, like there's just, and and
That's a
then
great kind of heat wave emergency tip.
right, and then same thing with hydration, like especially with seniors, they don't. The whole inconvenience of having to go have a pee is so they don't want to do that. For some people, it's very difficult to get out of a wheelchair and go to the bathroom, right? Or get out of bed and go. So they're very conscious about their intake, but that also then dehydrates them. And so
Right.
now they put cardiovascular stress onto their system. So the heart has to work harder because of the viscosity of the blood, blah, blah, blah. And so, going back to integrated design, right? People are part of our feedback system, and some of those feedback systems aren't operating optimally as we would normally expect them, right? So we have to keep our eye on that. So going back, the building owners, building managers with existing structures is you have to find out why these problems exist. A lot of it's architectural based, enclosure based. And then if you're doing modifications to existing buildings, for goodness sake, like one of the biggest problems is glass. Too much of it and poor performance glass.
Mm.
We know that 30-40% window to wall ratios, you get all the daylighting you need. It's much better for thermal comfort, much better for sound, much better for air quality. And people are going, well, what does glass have to do with air quality? Well, if you want something to break down, hit it with shortwave radiation. So if you think about particles and gases, right? You just let all that sunlight hit a synthetic flooring material, it's going to turn into particles and gases. So now you got an air quality problem, right?
Mm.
And so going back again to integrated design, when an architect and a client are figuring out, okay, well, how much glass do we want in a space, for the aesthetic look, you have to just say time out. Hang on a second here. Like there's consequences to this, right? And you have to be selective on window sizes, the performance of the glass, the coatings that we can put into windows to control the light, to control the thermal, to control, the sound, all of these types of things. So, and then thermal bridging. So for those that are following, maybe don't know what thermal bridging is. It's like if you're wearing a sweater and you've got this insulative layer in between the inside of the sweater and your skin, and it works great. But if you bend your elbow, right now the sweater's right up against your skin. Well, you've lost that air barrier. Well, thermal bridging is much like that. We have all of these structures, the studs, insulation between it, but the studs suck. They're not great at insulation. So moving the insulation or adding insulation to the exterior of the building so that we improve the enclosure, reduce the thermal bridging, and then making buildings tighter. Leaky buildings cause drafts, poor air quality, sound. Like there's lots of problems with leaky buildings. So when you're designing buildings, you do the processes, and there's lots of great materials and techniques to seal up a building.
Mm.
So you have to think about these things. Part of that, again, goes back to understanding, human physiology and psychology. What do people need? People don't need 100% window to wall ratios. There's no documentation that says you need to have all glass buildings.
Right.
Right. There's nothing that says that actually helps, the occupant. And you can, this is hilarious. Like, so for people, again, for your audience that are listening, you can take highly educated, very wealthy people living in these all glass condominiums that they spend millions and millions of dollars for, right? And inside those glass aquariums that they're living in, they've got all of their artifacts that they've collected from all over the world. They've got musical instruments, they got heirlooms, right? But then when these people travel, right, and then they go to the museums and they look at all of the artifacts and the heirlooms from decades and ages, thousands of years ago, none of that stuff is exposed to sunlight.
Right.
Right.
We've all got that partially faded carpet,
right,
where the fade line is like directly in line with where the sun gets to in the middle of the day, and then,
totally,
and then
right?
the other part of it's still fresh.
Right. So what happens to these intellectual people, smart, lots of money? They can make better decisions, right? They can go travel to any museum in the world and they can see how we protect these very valuable items, right? And yet they go to their own home and they destroy the stuff that they value. It's hilarious.
That's really interesting. Yeah, it's a conversation on psychology, and I don't know if ego is the right thing. It's just this notion of like views and curb appeal, and like status, and because a stucco wall, it doesn't say status, right? But an 8-foot by 12-foot piece of glass says status,
right?
And I can't tell you how many times I've been just recently, like in my own neighborhood, the old house gets bought, torn down, the new infill gets built. It's on the south side of the street. and the entire north side of the house is floor to ceiling glass, like on all floors, right? And
Yeah.
I'm like, we live in Canada, you know, this is not good for your heating bill. um,
No, like, so I've been to Dubai a couple of times, and it's funny because when you go back into ancient Middle East architecture, thousands and thousands of years ago, these were very conservative buildings, very small apertures, very thick walls. One building shaded the other building, and if you were the building that didn't have one next to it, they had a wall to shade it. Right? These walls provided also security, a way to keep their livestock and their children and and so architecture had a purpose. There wasn't refrigeration. We didn't have any of these mechanical interventions that we have today. So they had to use what was available to them at the time. That all changed when refrigeration was introduced into the marketplace, because now it enabled architects to use different strategies, techniques for their buildings and then you can actually see it. Like, you can see when refrigeration, mechanical cooling came in, and then the change in architecture that happened.
mm,
And so going back to Dubai, when Dubai was really developing its community of new buildings, new architecture, a lot of those buildings were based on North American principles, all glass, tall sky. It was all about competition, right? But today, if you go back, you can actually see vernacular architecture creeping back into their community because they realized that the old forms, the old architecture worked. It was
yeah.
simple, was not energy intensive, right? And this is where we need to get back to the roots of design. That the fact that we have an ability to intervene mechanically for a space does not mean that we should do it.
Right.
It's
Right.
actually
What's the
creating a problem.
priority? I remember somebody telling me years ago that they were from Europe and they came over here and they laughed. They were doing a lecture and they were laughing at us basically because he was talking about, we've got these sort of 12-inch, 18-inch thick, uh, uh, not adobe, what's the thatch, like kind of, and
Mm.
cob and this kind of stuff, right? and
Yeah.
and whereas here we've got these paper thin 2x4s, now 2x6s, but and all the houses are on life support. That was the analogy he gave, right? Your houses are on life support. The second you pull the plug, your houses die. you know
I
the
love that. I'm
pipes
going to write that
freeze.
down.
The
I'm going to use that. Who can I credit that to?
Oh, it was a long time ago.
Is
I'm
that
so
right?
sorry. I forget. It was actually at the public library. It
Oh, is
was
that
at the
right?
Calgary Public Library. This guy came in and
I
it was like
love
a
that.
straw bale kind of endorsement.
It's
And
true. It's so true. Our buildings are on life support. It is, yeah, because if you do remove the ventilation, the mechanical, the cooling, whatever, the buildings die.
yeah,
You
and
can go. You can go. So I was in Oman a couple years ago, and you're driving around, and you can see these old ancient villages. Like, these are thousands and thousands of years old, and they still exist.
mm,
That'll never happen with a wood frame construction building in North America. You stop the life support, it will die. I love that. That's awesome.
yeah, and you've hit on a couple of things, and I wanted to just let you kind of keep going. But I'd love to circle back to a few of them for some practical tips. So you
Yeah.
mentioned the awnings and the blinds on the outside, curtains, whatever it may be. So these folks that you think are doing it right, and that's in Australia, which is a bit of a different climate than we have here. So if you were to apply what they've learned and are doing from there to the Canadian context, what would that look like on a house? What does it look like on the south side? What does it look like on the north side? Or even a commercial building or school?
Yeah.
an office building. What are some practical ways? Because I'm assuming it doesn't necessarily function the same way year round. You might want some flexibility built in. I don't know whether that's on hinges or an automated thing. And going to like simple design so that we don't have as many things to break down. And yeah, so what would you say about that?
Yeah. So there, really, you should do a photo tour. If you can't get to Brisbane, for example, just Google Brisbane architecture, or Brisbane streetscapes or something like that. They've been so creative in so many ways. And just to give you a couple of examples, like you have, say, a multi-family, like a 5-story condo or apartment building with balconies, and they've got these movable partitions. So you can enclose the entire balcony, block all of the sunlight, or you can move the partitions over and let some of the sunlight through. They've got, rollable shades that are supported from the balcony above, and then you can bring the shade
And
down.
and are they 100% opaque, like dark room
Yeah,
styles, or are
yeah.
they do they still allow some light to come through?
So there's everything. I mean, just picture an inventory of 10,000 buildings, and with probably 70% of them having exterior shading. There's just the creativity has been awesome. So some of them are semi-opaque, right, or semi-transparent, so they can use like a weaving, sometimes you can get like blinds, people for North America, again, like interior blinds that you can order them up with different opening factors, right?
Yeah.
Or the fritting on a glass, for example. Well, the same thing there. You can get fabric that's quite open. You can actually see through it when you're perpendicular to it, but if you move to the angle, you can't see through it. To fully solid stuff. Shutters, that are like bifold doors, right? But you need to think in terms of bifold doors that can stand the exterior elements. These are not the
Right.
cheap bifold doors in your closet that you hate.
And even fabrics, right? And like we have so much MDF and
Right.
like what's a material that would be ideal for Canada, for to kind of get the right kind of thermal mass or the right
Fabrics,
kind of
like the canvases, like on awnings, these types of things. And even, there's like woods, metals, like there's just any materials. The thing is, when you get into some of these materials, they have coefficients of expansion, right? So whatever you're creating as a manufacturer, you have to be able to think about what happens when that you in the morning, like here where I am from in Alberta, right? So it can easily get, well, even today it was like 5 degrees Celsius, right? So, you get a 5 degrees C startup temperature, and all of a sudden it gets hit with a whole bunch of shortwave radiation. Well, the expansion on that, you have to think about that, right? So whatever materials you use, has to be able to not degrade due to shortwave radiation, right? So that eliminates some plastics, and it has to be able to expand, right? So fabrics
So
are,
the awnings are maybe a more affordable approach. The canvases, the various kinds of, maybe it's a poly type canvas, but you're expecting 5 years, 10 years, and then you're going to replace it. But it's a relatively affordable touch.
yeah. And so if you think about, um, and again, you can use sort of these passive solutions, or semi-passive, like the exterior blinds that you can adjust, this type of stuff. But then also just or landscaping, tree cover. It's just,
Right.
these are basic things that we use. Or you can go to the
Deciduous
very,
on the south side and coniferous on the
yeah,
north side.
just basic stuff, right? Or you can go, the extreme is, where you get into these earth homes, where they're buried in the ground, right? And they've got selective
Right.
exposure, for sunlight, right? Um,
Yeah, that really hasn't caught on here the way it
no,
has in Taos
yeah,
or other parts, of other southern U.S. and certainly in Latin America.
yeah,
Um, I suppose there's not as much profit to be made to the industry, with using kind of earthen materials or, um, yeah, we've gone down a different path for 100 years now, and it feels like challenging to unwind that.
yeah. When I think back, I do a lecture on the history of thermal comfort, and actually have happened to have some photographs of my forefathers who immigrated in the 1800s to Canada. And all the choices in the world, they could have gone to Hawaii or they could have gone, but no, they go to northern Saskatchewan. like the cold. I can't even imagine what it would have been like for my great great grandma and great great grandfather when first winters. It was just like, but the sod house, right? In the 1800s, people were living in sod houses in the prairies. We have pictures of that. And then, they would harvest lumber from the rivers, the valleys, and then they would make, wood framed houses. And what's interesting, but a lot of those houses still exist. You think about some of the old granaries, right? That are, but they're allowed to dry. Joe Stebrick, for those that are following again your guests, if you want a Canadian, and John Straub, there's two guys, legends, that understand the building sciences, and their mentors talk about old construction techniques that think about docks, wood docks that last a long time, and it's because they can get wet and then they can dry out. But anyways, the shading materials, the type of shading that we use, from the simple stuff like trees to movable partitions to fabrics, metals, woods, overhangs, basic stuff again, like overhangs. Like, what happened to overhangs? Like, there was a day, like, when you get you go down the street and the old traditional veranda,
Yeah.
big porches, overhangs, people that are in the rocking chair, kids walking on these are
Yeah.
great, Norman Rockwell paintings, these,
Right.
what life was like when we actually used good architecture, right?
Yeah, and that's interesting because even for myself, I like a good wraparound deck, but I found myself feeling like, oh, it's really dark inside. It's really dark inside the house because there's this 6-foot deck
Yeah.
on the south side, and then kind of moving away from it in my mind as something that's good because the interior is now dark. But how would you suggest kind of someone getting over that psychological sticking point to, like, look at the comfort, look at what that does for everything else in the home,
Yeah.
and putting that in a more positive light than.
That's where good design comes into play, right? In terms of looking at how do you use form to create these shaded environments, but still have natural daylight, access to natural daylight, that is the science of architecture instead of the
Mhm.
art of architecture.
On that basis, do you embrace things like sun tunnels so that
They're definitely
you're bringing
useful
the light into a
yeah,
room?
for sure. They're useful for sure. And, we, but you also have to remember that they can also mess with, like, too much daylighting at the wrong time of day messes with your circadian rhythms, right? So
Mm,
if you're going to put in daylighting into bedrooms, for example, that you want to make sure that you have a way to block that light off,
right.
right? So,
Right. And I suppose too, every time you're doing that, you're getting another penetration, another place for, a leak or air or
right.
something to happen there. And do you find that they are good for thermal, like, or are they actually bringing heat in as well that you don't want? Like, is there a trade-off?
But you do get some, but again, you're thinking of it more as because it gets filtered, right? So you're not, so again, depending on the performance of the glass on the roof, you're going to get some shortwave radiation through, but a lot of the infrared gets filtered out. You know, you,
Hmm.
so you get the light, but not necessarily the intensity of the heat. Right?
Yeah, I
So,
mean, certainly I have lot of, fond memories of my cottage as a kid. Big skylight
mm,
in, like, just over the kitchen dining room, and it's so beautiful. You can see the trees out from it and everything. But in the middle of the day, having lunch, that dining room was just cooking.
yeah, right. Yeah.
I think we did end up adding like a a channel, because it was on an angle sloped roof, so we had a channel, and then we had a set of like blinds that would come down and sort of droop,
Yep.
but of course on the inside.
Yeah.
uh,
Yeah.
so it did a little bit.
Yeah. Skylights are they're a beast all onto their own. But there's some brands out there that are well recognized that have done a lot of work in the skylight sector in terms of lighting and heat, these types of things, and color, because they can filter out. So I'm not sure what the brand name policy is here on your podcast, but
Well,
everybody
if
will.
there's anybody you want to shout out, I'd say that's let have at her. I
Yeah,
don't know how much we'll call out, but
yeah,
yeah,
yeah. I mean,
shout
so
outs
like
all good.
what I like about the Velux brand, what I like about them, again, not necessarily an endorsement for their product, but I do endorse the amount of research work that they do. They are a world leader in looking at indoor environments, lighting, thermal, sound, all of that type of stuff. So it's not that they're just producing product; they they back up, the story
Mhm.
that they're telling, and they've got software tools that allow you to model spaces with their lights. You can actually see the lighting profiles that are created. So I really like, and again, I like the manufacturers who back up what they're selling, and and we see this a lot, like particularly lately with the heat pump manufacturers or the thermostat manufacturers. And a lot of people know that if you've been following me, I take issue with a lot of phrases that we use to convince people to buy stuff. Like, if you buy our heat pump, we're going to make you comfortable. You can't make people comfortable. You can't make someone feel something that they don't, as
Mm.
if they have no other part in the equation, right? Or we're going to make the room comfortable. How does the room know it's comfortable? Like, where's the feedback mechanism that tells us that the room is comfortable, right?
Mm.
It's about the person. And so you can't make somebody comfortable. You can't make a room comfortable by putting in just a piece of equipment. Isn't going to make a difference if you haven't considered all the things that make people experience a space. So what we say correctly, technically, is that as designers, we can create the conditions for people to sense, because people first sense and then they perceive and then they react to the environment. So all we can do as practitioners is create the conditions for people to first sense and then perceive thermal comfort. And then if they are in a discomfort mode, then we have to give them the ability to adapt. So the ability to change clothes, open a window, put on whatever, right? Turn on a fan, these types of things. But the adaptive methods that we create, we make a lot of assumptions. So it's easy for somebody who's able-bodied to be able to open a window. But if you've got really severe arthritis, for example, or you're wheelchair bound, right? Well, all of a sudden opening the windows can be very difficult. So we have to
Yeah.
think about, all right, we're going to create these environments and we're going to build in adaptability, which is good, but can people actually take advantage of that? What is their physical capabilities, their psychological capabilities to be able to physically adapt? And some people don't have it.
Mm.
I'm thinking people have Parkinson's, for example, or multiple sclerosis, right? Or some other ailment that prevents them from being able to adapt to their environments physically or mentally, right? So it's we have to think about these things.
Absolutely. That reminds me of a gentleman that I know. He's an old timer, bit of a salty dog. Has been
I
in
like
the
them already.
trades he's been in the trades for the better part of 50 years. Um, has seen all kinds of stuff, and he was helping me do some work on my house a few years back, and I was like, oh, it's always cold and kind of drafty over here. Like, should we chew the windows? Like, what should I do? And I never forget his comment was basically how, going back to Europe and something hundreds of years, the house would breathe. You designed the house to breathe. Like, it was okay to have some drafty spots. He positioned it as, you kind of want to have different climate zones within your house so that you can change your, like, put on a sweater if it's cold, put on this, like, there's pictures of people wearing like the full long johns, right, and a water bottle in the bed. And I don't know if we want
Right.
to go all the way back to that, but he was essentially espousing the benefits of having different parts of your home feel a little bit different, so that depending on where you're at in the day, whereas now the mentality is like, I want to wear a t-shirt and shorts
Mm,
no matter
yeah.
what. And we try to morph it. Like, what would you say to, someone who's got that kind of, mentality versus where we do everything super airtight and we're almost inside a plastic bag?
Yeah. So there's a term for that. It's called allostesia, and it's actually it's exercising the body's sensory system, much like an athlete who has an incredibly good balance. Well, how did he develop that incredibly good balance? It was by being out of balance and recovering. Right. So when we get into stagnant environments, we're not exercising our sensory systems. So an example of that is, as again, when you're outside, you're walking down the street, you're really hot, you're sweating, and you enter a space that's been conditioned with air conditioning or cooling, and there's that like relief, right? It's that's going from one state of experience to another state of experience that provides the pleasure until the space gets too cold, and then you got to put on a sweater, right? But that's
Yeah.
what that's all about. And you know there's standards for indoor environments, and one of the challenges that we have right now as our industry is getting building codes to adopt these standards. So one of them is ASHRAE Standard 55, which is thermal environmental conditions for human occupancy. And that standard works on 11 different factors. So again, going back to my comment about air temperature and thermostats being a poor proxy, the reason for that is because air temperature is only one of 11 factors. And so what we want to do is we want to make people aware that are in the design community, the construction community, and even the general public, that thermal comfort comes as a result of creating conditions. That's why it's called thermal environmental conditions for human occupancy. That's if it was called air temperatures for comfort, we would have called it that, but that's not what it's all
Right.
about, right? So where am I going with this? When you read the National Building Code of Canada, there's a statement in there that living conditions shall be able to maintain 22 degrees C or 72 degrees Fahrenheit air temperature. Right. So going back to your comment about your colleague there, the salty old guy having these different climate zones. Well, the Building Code of Canada doesn't say that. It says that you shall maintain 22 degrees C. It's not a thermal comfort statement. There's nothing in our standards that support a set point of 22 degrees C as being something that's thermally comfortable. There's no statement in the world of any research work, right? So why does it exist? Well, if you go back into the National Building Code of Canada, it says that the code is there to limit the probability of someone becoming ill, right, due to thermal conditions, not creating thermal comfort.
Right.
There's a big difference between preventing someone from getting ill and someone from feeling comfortable in a space. Those aren't even on the same planet.
Sure.
Right. So, but how do people design buildings? They have to design it so it's compliant with the building code. So they use 22 degrees C as the witness that they've complied with the code, not that it complies with thermal comfort standards.
Interesting.
Right.
So yeah. I know even in my own home, thermostats on the main floor, call it 21, I'll set it at. Upstairs is tough for sleeping because it doesn't feel like 21. Because when I'm on the main floor, it's pretty good. And then if I go down into the basement, it's like sweater time.
Right. So So that's an element in the standard. We look at stratification. Like we want to know what the temperature profile is across the person, right? And when you have stratification within a building, that has a lot to do with, again, the leakage of the building, because you get stack effects, right? Pressure differentials, where the pressure plane is in the building. So we can design all of that out, but still provide diversity, thermal diversity in a space. Zoning is one of those techniques, right, that allows us to have diversity. It's really easy to do with hydronic systems. Zoning is like, that's just like standard stuff, right? There's no magic to zone in a hydronic system. And that's just like, you wake up in the morning, and if you're a hydronic system, you just know that you've got a whole bunch of other colleagues in the room with different thermostats everywhere, right? So
years ago, sorry, go on.
Yeah, so it's pretty easy to do with hydronics. Forced air systems, they've been trying for years. Like we get commercial buildings, you can get zoning, VAV systems, but residentially, it's a bit of a challenge, to get zone systems and forced air. Not, it's not a challenge for hydraulic systems, but anyways,
Yeah, certainly on a retrofit basis. Like on new, you've got the opportunity. It's a blank
right.
slate. On a retrofit basis, um, do you see a lot of people moving to hydronic? How, like that? It seems a little more challenging to pull off.
Yeah, it's
What would you say to homeowners who are looking at doing a major
yeah.
renovation to their home? What kind of recommendations would you give them?
I have a huge bias. I'm going to just put that out there right now. When I got out of school in 1983, I had a really great mentor, and our designs were always based on hydronic radiant floor heating. So let's go back into the 80s, and a separate system for ventilation. So back in the 80s, we were using heat recovery ventilators. Well, back then, it was energy recovery ventilators. People
Right.
thought that
Wow.
HRVs were here first, but no, no. ERVs were here actually long before HRVs came down. So there's actually patents were filed in, I guess it was 1997, I guess is when the,
And just
no,
for the audience, the difference there being the humidity
right.
exchange.
Yeah, so on the ERV, the heat exchangers perforated, I guess is a good way to look at it. People can understand perforation, but allows you to transfer moisture back and forth. Where on an HRV, there is no perforated heat exchanger. It physically is just sensible heat only, right? So, but yeah, so back in the 80s, 83, 84, we were using ERVs and then HRVs, and then we went into heat pipe systems, blah blah. Anyways, so separate systems. And so going back to your question about if I was, people that are renovating or restoring their houses, um, a lot of it depends on the performance of the home. If they're not planning on changing the performance of the home, like in terms of upgrading insulation, blah, 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 and if it was a fairly sophisticated buyer client, I would definitely be putting in a separate system for thermal comfort and a separate system for air quality. I wouldn't try to mix the two.
Hmm.
And I would definitely look at doing a hydronic system. And if they've got an existing furnace, for example, I would maybe convince them to try, or not convince them, but I would certainly take them down the path of an air to water heat pump. Use their existing furnace. If they've got gas, put a water coil on top of it, right? And then use the heat pump water as opposed to using air, because then you could use that water to do domestic water heating. If you've got places in the home that have been uncomfortable, you can add panel radiators. You could do floor heating in your kitchen. You could do floor heating in your bathrooms, for example. There's these things that you
So
can do.
that
This, yeah.
the air to water heat pump can be synchronized or integrated with an existing furnace, an
Oh
existing
yeah.
gas furnace, so that now you're using that furnace less. The heat pump's
Yeah.
dramatically more efficient.
Yeah.
Am I getting
And
that right?
yeah. So, but again, the efficiency is yes. So you definitely have more efficiency, but you also have to look at where's that power being generated too, right? So when you're in British Columbia, Manitoba, parts of Ontario, the east, where we have a lot of hydroelectric. The marriage of hydroelectric with a heat pump with heat exchangers, like it doesn't get much better than that. In our
Mm.
lifetime, that is nirvana. Like that is the place we want to be. Here in Alberta, we are determined to suck the last cubic bit of vapor out of the gas hydrocarbon out of the ground before we jump on to renewables. Although we are seeing more and more of
It's
it here,
getting
but
better, yeah.
it is getting better. But so um, and this gets back into again engineering principles and without getting too technical here, when you talk about heat pumps and we talk about this term coefficient of performance. So what you put in, what are you getting out, right? So the traditional expectation is that we could put in one unit and get out 3 units. That's a pretty common expectation. But when you can take renewable energies with a water to water heat pump, like a geothermal system or ground source heat system, and marry it to really large surface area heat exchangers, either like a radiant floor heating system or an oversized coil and an air handler, then you can get the temperatures down in heating and up in cooling. And now all of a sudden those COPs, they can go to 5 or 6.
Really?
Oh yeah. So you think about it. So if you take, for example, a ground source heat pump in a high performance building using radiant floor heating, we're heating those spaces with fluid temperatures that are like 80, 85 degrees Fahrenheit, like lower than body temperature, blood temperature, right? And the return temperature coming back to the heat pump is going to be somewhere like in the 72, 75 degrees.
Mm,
So the coefficient of performance, a very little lift, what we call the lift, like what's the temperature
right.
change, right?
It's
And so
barely
because
working at all. It's like
it's
sipping.
right, so you're just the COPs go way up. Well, why that's important is that as we're on a continuum right now, this energy continuum that we're transitioning systems, and the velocity of that change is heading towards electrification, decarbonization. That's where it's going. And if we achieve that with only COPs of 2 or 3, the demand on the electrical system has to go up. Like there's no choice, right? But if you can design your mechanical systems in conjunction with your architectural systems and get these low temperatures in heating, high temperatures in cooling, and now you're, instead of having a COP of 3, you're getting a COP of 6, that changes the entire electrical profile on the
Right. We
continuum.
might not actually have to
Correct.
expand the grid quite so much. It's cheaper to
Exactly.
save a megawatt than to build another one.
Absolutely. And so this is why I hope everybody's getting the idea here that this, when we started the discussion, we talked about integrated design, and I pulled in why it's important to have people as part of the equation, because when we use people to design the architecture and the enclosure, the interior systems, mechanical systems, we get these low loads. So now we're preserving energy and conserving energy. And then when we condition these spaces with large surface area heat exchangers with heat pumps connected to renewable systems, well, now we're getting, and I'll try to avoid using technical terms here, but we're getting less wasted energy. The energy that we do convert gets used more. More of it's used. And so there's this term we call exergy efficiency. Everybody's heard about energy efficiency, but what's more important is actually this term called exergy efficiency. It's the way we can wring out the work of an energy conversion, right?
Mm,
So to put this into more practical terms, let's use money, for example. Most people, if you had something, let's just say, for example, this therapy ball. I'm an old guy. I have to do stuff, right, to keep my body working, right? I paid probably $10 for this ball for doing therapy work. Um, why would I pay $100 for it if it's only worth 10, right? So, and in fact, the reality is it was probably made somewhere for like 50 cents. So, in terms of exergy efficiency in energy systems, you can have exergy efficiency in currency systems, where it says, well, if this thing costs 50 cents and I paid $1, okay, that's not a bad deal. If I paid 10, that's not great because I paid way more money than what it's actually worth. If I paid 100, then I'm just being stupid, right? Well, when we have natural gas, when you ignite natural gas, it turns into a flame temperature of 3,400 degrees Fahrenheit. Well, if you only need 70 degrees in your room temperature, 70 to 3,400, that's like me paying $100 or $1,000 for this ball, currency
mm,
wise. So why are we doing such stupid things? There's
mm.
places that we need 3,400 degrees, steel production, power production, these kinds of things, moving ships across the ocean, flying planes, these types of things. But those are industrial applications. Heating houses, buildings, that's a non-industrial application. We don't need to be creating 3,400 degrees to condition spaces. So
Interesting.
going back to renewables, they don't produce these high levels of energy. And so we have a lot less waste. Currency, if you were thinking in currency, if this thing costs 50 cents and I paid $1, great. I've just saved myself $9. I can use that $9 for something else. If I paid $100 for it, like that's a quick way into destruction and personal destruction, right?
Yeah,
So yeah,
you mentioned heat pump, air to water or ground source. You mentioned high surface area heat exchangers. So I'd like to unpack that for a moment.
yeah,
Um, in the Canadian climate, HRVs versus ERVs, and are you suggesting sort of maybe a larger heat exchanger than what might the industry might normally be selecting, because like you really want to kind of oversize it to the house or to
yeah.
the building?
So yeah, what you want to do is you want to work backwards from the machine. So if the heat pump can actually achieve a COP of 6, what conditions do you need to make that machine get that COP of 6?
Okay.
Right? So you have to work backwards from it. So that means you have to think, okay, well, how do we get the temperatures down and heating up and cooling? So then you have to look at the building load, and then you have to look at the size of the heat exchanger. And so now we're getting into engineering crap, but
Right.
that's
It's like shrinking the delta.
right. Right. So I don't know, for those that are maybe, um, that don't have a technical background or engineering background, it's like if it's a trade-off. If you have a small heat exchanger, then you need a different temperature profile. This is actually what happened in the past with old buildings. If you say, for example, you take an office building that was built in the, I don't know, whatever, the 30s or the 40s, and they are typically heated with steam or hot water, but these heat exchangers were very small, like baseboards, right? Or fan coils, you'll see them, or panel radiators. Well, because the building sucked and they used a small heat exchanger, you needed the temperature of the steam or the temperature of the boiler running at 180 or 190 degrees because the heat exchanger was so small, right? But you get into these, like, for example, if you go into the Calgary International Airport, next time somebody flies through there, the international, that's all radiant heated. All those surfaces, the floors and the ceilings are heated or cooled. Well,
Mm.
they're using like 85, 90, 95-degree water temperatures, 100-degree water temperatures to
And
condition those big spaces.
they're running those through the slab.
Yeah. Slabs are in the ceilings, depends on what part of the building.
So in a ceiling like that, in a commercial context, is that just your T-bar and they've got kind of
Yeah.
loops
So just picture an
suspended up there,
aluminum
or how do they do
panel.
that?
Yeah. So it's just an aluminum panel with copper pipes on the back side of it. And then they just run chilled water or heated water through the panel. And of course, aluminum is really conductive and it just either absorbs or releases
And
energy.
they hang that from the
Yeah.
ceiling, like using like U channel or
Yeah,
something,
you
or
can, and you can just, when you're walking down the corridor, just look up. You can just see the panels and you can see all the pipe connecting them.
right
Yeah.
on.
And then and if you go through the international section on the departures lounge, you'll see like these pillars. Often they have a monitor on the top, but you'll see this perforation in the pillar. That's actually displacement ventilation. Air is actually coming out of that perforated area because it's all of these openings and it's so big, the air coming out, you can barely feel it. But if you get
Hmm.
up there close and you lick your finger and put it, you can actually feel the air coming out of that, right? Which people look at you kind of weird, but when you're in my world, that's the kind of stuff you do, right? You have to be able to put up with the weird looks because you're actually right. And then you'll look up and you'll see ceiling fans. So in the Calgary National Airport, they have radiant heating, radiant cooling, displacement ventilation, and they use ceiling fans for elevated airspeeds to help in terms of the environment. Creating, having some air movement, but also to improve the heat exchanger. Yeah. Anyways, we'll get into some
To
engineering stuff.
destratify the space,
Destratify spaces. Yeah. Yeah.
right?
Yeah.
Um, that actually reminds me of something you said earlier about the manufacturers and getting behind their products and kind of modeling things. And on the modeling side, you know, we use Red Screen a lot in our work. There's other programs. One of the things that's very easy to do is to say, "Oh, I have this piece of equipment now. I'm proposing this piece of equipment. The efficiency goes from this to this. Therefore, my savings are this because my schedule is this."
Mm.
When it relates to passive design and putting a tree in the yard or putting an awning on the window, that starts to get a little bit trickier to try to position it as an ROI thing, even though like we know that it's going to do that.
Right.
What would you say to folks there? Because a lot of the time these upgrades have to be pitched to ownership. They have to see the financial numbers, show me the numbers, why would I care, 2-year payback, whatever it might be. um how have you gone about?
Well, the first thing we would do, like in terms of changing out equipment, is again the the published efficiencies in the literature means absolutely nothing unless you can get that equipment to perform at that condition.
Right, there's always an asterisk that says, in these laboratory conditions, when this temperature, this humidity, or like lighting, for example, is
Yep.
always really, really narrow.
Yeah. In fact, it's fraud when you have a lot of people, and again, like, and I use that word deliberately because if I'm like, Joe and Jill consumer, and I am not a technical person, and I'm someone, and I need to replace, for example, my boiler or a furnace, whatever it is, and someone comes to me and says, if we change out your boiler, which is whatever, say 72%, because it's an older boiler, and we put in the new boiler, and you're going to get 98%, and there's a return on investment, blah blah blah. Like, I'm going to buy that pitch, but if I'm an engineer, I'm going to say, oh yeah. How am I going to get 92% out of this boiler? Tell me how I'm going to get there. And if that person can't tell me how I'm going to get there, like, I'm going to slam the door in their face. I really am. Because to get 92% or 95% out of a boiler, that water temperature coming back to the boiler has got to be like at 72, 75 degrees Fahrenheit. Well, if my heating system is designed for 120 return, how the hell am I going to get 92 or 95% out of that boiler if that's what it's designed for?
Mm,
Right? So
right.
you people that are going in and they're upgrading or telling the consumer to buy this piece of equipment because it's going to have a higher efficiency and there's going to be return on the investment, prove it. Like, tell me the story, because you just don't get the change by swapping out the equipment. You have to change the operating conditions for it to achieve that, right?
Yeah.
People don't know that. And so when you're doing that, you're not telling the whole story, that's fraud.
So the going back to the kind of an order of operations or certain things you might look for first to try to create the conditions to be a riper environment for that heat pump or that exchanger,
Yeah.
HRV, ERV to work at its best. Um, what would your approach look like with the client?
You would do an audit on the building. So you'd actually get in there, do a survey of what the building's all about, get the energy bills, like a historical trend of energy consumption, and then look at the operating conditions. How is the mechanical system set up now? Right. And then from that information, you're going to be able to tell whether the heat exchangers, the panel radiators, the fin tube, whatever it is, if it's an apartment building, right, whether they're big enough to run at a lower temperature. Right. Oftentimes back in the past, there was an oversizing factor that was done. Nobody thought anything about it. And to some degree, it's actually working in our favor now as we convert buildings over. Some buildings not, right? But that's why you have to go in and you have to survey it, right? If the building has had modifications to it, for example, so you haven't changed the mechanical, but you've changed the enclosure. So you've changed out the windows, you've added some exterior insulation, you've changed the thermal profile of the architecture. Well, now the loads are less. So maybe what's in there for the heating system is actually fine. You can actually run it at a lower temperature without doing
Mm,
anything. Just somebody needs to change the control setting. So it could be
yeah,
something very, very simple or something that's a little bit more complex.
we certainly have experienced a number of instances where the set points just could be better.
Yeah,
Something's on 24/7, doesn't need to be.
yeah,
That happens all the time.
yeah,
Buildings aren't commissioned properly. Like we've been
yeah,
in. I won't say the certification because I won't give them a hard time. But there's certain buildings that are sort of a standard that is very eco-friendly
yeah,
considered, and the occupants themselves, like it won awards. It won a high standard and whatever, got all these points. But the occupants were not very happy. They had like very hot, very cold, adding heaters, adding coolers, like in different parts of the building, which was quite strange. We were really surprised when we walked in and saw that. And it came back. It sounded a lot like just not tuning it quite right.
Well,
out the gate.
so I can tell you, because I sit on a number of standards and committees, and some of these building programs refer to the standards. So, in other words, to get certain points, you have to be in compliance with all or part of the standards. Many of those buildings receive points, compliance with the standard based on graphs, not doing any math. And the graphs basically were used as dartboards. So in other words, if they could throw the dart and it landed somewhere within the zone, then they would say that that they were in compliant with the standard, and therefore they were eligible for the points. Right? No one said, well, the building, the architecture, enclosure, interior system, mechanical systems, the operation of that does not represent the graph, or the graph did not represent the reality. Like, nobody questioned that. They just said, well, no, according to us, it's going to be here, and so therefore we're good. But in that process, somebody forgot to say, well, there is actually going to be a feedback loop. It's going to be the people.
Yeah. That's really interesting, because in our program, we work a lot with Indigenous communities. And, a big theme constantly is around prior informed consent, engagement, like, come talk to us. Like, we want to be involved. We don't want to just be told. We don't want to, have, and it just sounds like that's universal. And yet it feels like, we might be missing those opportunities all over the place, not just in those communities.
Absolutely. Yeah.
Kind of designing in a silo.
Hey, just out of curiosity, to take a sidebar here for a second, do you know Oralee McPherson?
No.
McPherson Engineering? Do you know about the Blanket of Warmth project?
No, I don't.
So Oralee, what a wonderful woman.
We'll have to have her on.
They developed this mechanical system, and it was for Indigenous communities where they were having bad mold problems, particularly in basements. And so they went in and they put in these radiant walls in the basements, and they used the existing furnaces actually to heat the water. Believe it or not, it wasn't a water to air; it was an air to water exchanger. And but by heating up the walls in the basement, they changed the dew point, so they weren't then condensing. So it got rid of the mold, but then it also improved the thermal comfort of the space. They actually ended up winning some awards, and so, and she'll be the very first person to tell you, I'm not an engineer. My husband's an engineer, and they have an engineering company, but I am a representative of what we can do for communities that are struggling with their environments, and so they've got this Blanket of Warmth project that they've done, and they're doing buildings, and they're winning awards, and they're talking about it. And it's a micro example in a very macro world, but it's making a difference,
Yeah. Well, Robert, I want to thank you for your time.
My pleasure.
I'm going to have to cut this one off, but I feel like we could go for hours here. So I think I'm going to have you back, and we'll dig deeper into a bunch of other stuff, because we didn't touch on prefab today at all. And I really would like to really dig into that as well with you.
Sure.
There's so many ideas here. But I want to just, it's been a real education. And before we wrap up, I just want to give you an opportunity to kind of maybe let listeners know how they could get a hold of you. Are you still involved? Or I know you're semi-retired, but it sounds like you've got too much going on in there to kind of keep it from everybody. So
my son says I suck at retirement. I'm very good at many things in my life, but I suck at retirement.
Well, and that's a compliment, because I think for people who really enjoy what they do, you never work a day in your life.
I haven't. I have not worked a day in my life. And my dad, early in the program, we started talking. My dad said, "You're basically unemployable. You're never going to get a job with somebody," and he was right. And it was the best advice he ever gave me, because I never have worked a day in my life. Every day has just been a joy, and learning and sharing and working all together. So I am on LinkedIn. That's the best way to get a hold of me. If you send me private emails or requests, I got to tell you, I got like a lineup like over 3 years old. I just can't get to everybody. But if you post something publicly, then I will participate, because my participation on a public forum, everybody learns. If it's one-on-one, I'm going to charge you for it.
Right.
So
Right.
that's the best place to get a hold of me. I am still doing a little bit of volunteer work for ASHRAE. My days as a distinguished lecturer are coming to an end. So if you saw me in the past, great. If you ever see me again at a conference, it's probably because I'm getting paid.
And are there some sources of your material online where people can go and maybe listen to some of your previous lectures?
Yeah. So most of the conferences will have, like Building Knowledge Canada, have all my lectures available. Many of the ASHRAE chapters will have actually video recordings or audio recordings of my stuff. There's papers, journal articles, all of that's available. At one time, I had a website. People are hounding me to put it back up again. I had all of my lectures for like 25, 30 years were there. I might actually create an archive that people can get that access to that stuff. But it's out there. Yeah.
Great. Well, Robert Bean, thank you so much. It's been a real treat. I've learned a lot today, and I really look forward to having you back on when you've got some time.
My pleasure. Thanks for having me on.
Thank you.
All right.